So gas molecules travel in a straight line until they run into something. How far do they travel before they run into something? The average distance between collisions is called the mean free path. So mean is another word for average. The free path is how far does it go before it runs into something. So the mean free path is going to decrease as the pressure increases. So we've got these particles zinging around inside this container. If the pressure is higher, then they're all squeezed together more closely. They're going to run into things more often. Their mean free path is going to be less. So if nitrogen was the size of a golf ball, it would travel about 40 feet between collisions under a typical pressure, temperature situation. The process by which gas molecules spread out. So diffusion is when gas molecules go from an area that's more concentrated to an area that's more diffuse or lower concentration. So I have 5 sons, and so there's an awful lot of gas passing in my house, you can imagine. It's not just the stench of testosterone, we also have gas. So if you think about someone farting quietly in the corner of the room, right? Isn't this fun? You know, and that person smells it, and they're going to pretend that they didn't hear anything, they didn't do anything. But eventually, that smell gets everywhere, right? How's that happen? Do you ever wonder about that? Farts have gas, they're gases, right? That's why we say, oh, I got gas. Yeah, when you fart, the gas comes out. Sometimes those gases have an odor. The gases spread out like all gases do to fill their containers. So right where that person farted, you have an area of high concentration of that gas. And diffusion is the process by which it spreads out, ultimately into the entire atmosphere. How about that? Your farts, all your past farts, completely spread out in the atmosphere. Could be proud of that, I suppose. So that's diffusion. High concentration to low concentration, it spreads out. We also have situations where gases can escape through small holes, technically through a small hole into a vacuum. This is called effusion. The rates of effusion and diffusion are both related to the average velocity, the root mean square average velocity, which kind of makes sense, right? If the gas particles are moving faster, they're going to spread out into the room faster than particles that are moving slowly. So for gases at the same temperature, the rate of gas movement is inversely proportional to the square root of its molar mass. The rate of movement is proportional to its velocity. We had that equation, the root mean square velocity, is the square root of 3RT over m, where this is molar mass. So we're saying the rate of gas movement is inversely proportional to the square root of the molar mass. So that brings us to Graham's law of effusion. So Graham is the guy who came up with this. So for 2 different gases at the same temperature, the rates of effusion, if we express them as a ratio for rate A and rate B, those would be equal to the square root of the inverse ratio of their molar masses. Here we have an illustration showing effusion. So here you have a gas, and here you had a vacuum. And there's a little hole here. We know from experience that if you have a balloon and you make a little hole in it, maybe you manage not to pop it, but there's a little hole in it, what's going to happen? The gas comes out. Like, well, duh. How exactly does that happen? It doesn't pour out like a liquid does. What's going on, little tiny hole, these gas particles are just bouncing around like normal until one happens to have a path that runs straight into the hole, and it'll leave. But the rest of these are just there, bouncing around, until they happen to hit the hole, and then they can escape. So the rate at which they do that is going to vary depending on how fast they're moving, and that is related to their molar mass. Helium escapes from a balloon faster than air does because it's smaller in size. And it's not because the helium fits through the holes in the balloon. You ever wonder why? Why do balloons go flat? Because the latex has tiny pores in it. And so the gas molecules, air, oxygen, nitrogen molecules, or the helium molecules can fit through the holes. But in order to get through the hole, they have to be on a path, a target to hit right at the hole. So most of the time, they just bounce off, they miss the holes, they stay in the balloon. Helium balloons go flat faster than air balloons because helium is smaller and it's moving faster. If things are zinging around this really fast, they have more chances to hit the hole and escape. If they're just lumbering about, going really slow, then just chance they're not going to hit the hole as frequently, and so they will effuse slower. Does that make any sense? So I'll give you this equation too, because that one's kind of hard to remember. When I skip the whole derivation of all of that, if you're interested in that, it's all lined out very nicely in your book, and I'd be happy to discuss it with you if you want. Find the ratio of effusion rates of hydrogen gas and krypton gas. So we need Graham's law of effusion. So rate A over rate B is equal to the square root of the molar mass of B divided by the molar mass of A. Well, we've got hydrogen and krypton. So instead of A, I'm going to call that one krypton. No, I want to put helium on top. Hydrogen on top, hydrogen on the bottom. And over here, instead of B, I'm going to make that krypton. Hydrogen's going to have a faster rate, and so if I put the fast rate on top and the lower rate on the bottom, then I'll have a number that's greater than 1, and I like numbers that are bigger than 1. So that's the ratio we're looking for. So we need molar masses. Now that capital M was in kilograms per mole. When we've got a ratio of these two, does it matter if we use grams or kilograms? No, because the units cancel out. So if we have grams per mole on top and grams per mole on the bottom, the units cancel. If we had kilograms per mole and kilograms per mole, they would cancel also. So here we don't have to worry about that. Molar mass of krypton, 83.80. Molar mass of hydrogen, H2, remember, 2.016. So the square root of 83.8 divided by 2.016. So this ratio is 6.447. No unit. What this means is that the hydrogen gas effuses 6.447 times faster than krypton. Any questions?